Okay, so let's get started. This is the first exam. You may want to, again, maybe come in so you can see the screen better. Everything is kind of on screen so that we can move fast because we've got a lot of ground to cover. There's a lot of stuff in this. And I think we'll just start off a little different than the book does. Start off with a description of what's called simple harmonic motion. The idea is you have a block going back and forth, something like mass on a spring. You can think of that. Very often we get talking in terms like omegas and phis, all this angular stuff, and you say, hey, we're just going back and forth. What's all this angle stuff? The idea that there's going to be some angle in here as this thing goes around. And simple harmonic motion, maybe I'll hit that play one more time, is one where this thing is going to go around with a constant angular velocity. So it's not just any old back and forth. At a constant angular velocity, the shadow on the x-axis is going to line up with the block that's going back and forth. So if we want to describe that top block with simple harmonic motion, we can do it with kind of this abstraction for angular velocity. Now this particular angle here is changing with time. And well, first of all, the amplitude of this thing is going to be equal to the radius of this circle. And the motion, we're just worried about the x-axis. That's going to be a cosine omega t plus phi. Oh, by the way, we can play this whole game also on the y-axis if we want to. And then we'll have a sine here. So you'll see it in a lot of homework problems you had, wow, it's either cosine or it's a sine. They really differ by some angle phi. And in fact, this angle phi represents the position of this thing on this circle at time t equal to 0. So let's say right now if I'm going to be starting this thing and I hit my stopwatch here, this initial angle would be phi. Very often we have the choice of where we want that angle, and it's usually just convenient to say, oh, when it's down here or the mass is clear over at its amplitude, we'll just start our clock there. That's convenient. And then phi is just 0, and you don't have that term banging along. Some homework problems, they kind of force you, the way they set it up, to kind of adopt something where you have to consider what the initial condition is relating to that angle. Okay, anyway, so the description of the motion is given x is equal to a cosine omega t plus phi. Again, omega t plus phi is going to be this angle that's going to be going around at a constant angular velocity. Just taking the derivative with respect to time, this cosine becomes a minus sine, and then we have to go with the chain rule, come up, and that is going to pull out an omega. So most of you are familiar with this kind of stuff. If we want to deal with acceleration, we just take the derivative one more time. Then we end up with minus a. We have an omega. We're going to get another one when we go from sine to cosine, and the chain rule. Going to bring another omega out here, and we're going to have an omega squared. So this is the kind of the mathematical description of simple harmonic motion. This term out front, consider all this cosines and sines, they all just vary between plus and minus 1. This term out front is going to be the amplitude, that's the x motion. If we're talking about velocity, it's this whole thing. This goes between plus and minus 1, and so the amplitude of that, or this, is v max, the maximum velocity. And also the maximum acceleration is this. So, done a lot of problems. You should be familiar with this stuff. The idea of the angular velocity, very often we want to relate this to a frequency or a period. I like to start with this as sort of my mantra for keeping this stuff straight. The angular velocity, or the angular frequency, is equal to 2 pi times the frequency. Frequency is the number of cycles per second, and then there's 2 pi radians in each cycle, so that is this angular velocity. And then frequency, just flipping this here, is probably the more convenient form of this in terms of calculations, is going to be just omega over 2 pi. And then we also have the idea of period. period is equal to 1 over f. You want to get used to that. Frequencies is cycles per second, but period would be seconds per cycle. So they're just reciprocals of one another. And hopefully that makes sense. Okay, so again, this, yeah.
I was under the impression that acceleration, the negative canceled out because you were going from a negative sign to a negative cosine.
Okay, we take the cosine, take the derivative, we get a minus the sine. Then we take the derivative again. The minus is still there. This, but now sine to cosine, we don't have a minus. Okay.
So you just pull the minus out.
We just have that minus. It continues up from above. So yeah, just the one minus.
So it's not the derivative of negative sine, it's the negative derivative of sine.
Right. Hopefully does that make sense mathematically? Now we're going to have some other negatives come in here, so you're maybe thinking ahead is maybe what you're doing. But this is just really the mathematical description of motion, which we're calling simple harmonic motion. There's really no physics here. This is just kind of our mental image of this kind of motion. Now, we have to deal with a particular physical situation. And here we're going to start with a mass on a spring. This is the classic place to start, where you got a frictionless surface. We've got a spring that is going to be relaxed when the mass is here, we say at the origin. That's where x would be 0. When we pull it out this way, this force, we dealt with this back in 121 where you're introduced to the spring. We said its force is equal to a minus kx. That minus sign indicates that the force is going in the negative direction. That's nice. This equation is good for us even when we're on the other side. When we're back over here, x will be negative, and then a negative x times a negative k will be a positive. So there's going to be a force back in this direction. So this really describes the force of the spring on either side of this thing. This is what we call Hooke's law. And what we'll do is start with this idea. Usually you think conceptually, if this thing was in front of you, you might take this thing and you pull the block. You could pull it to really any amplitude that's within the elastic limits of the spring, but you can pull it out here and then you release it, and then it's going to start to oscillate. Out here it's going to be at rest when you release it. It's going to then, with the force of the spring, it's going to be pulling, accelerating. It's going to fly through the origin, and then it's going to go out and come to rest out here and come back. So I think you've seen enough of this that it's pretty obvious. Now let's kind of do the math on that. We're still with good old Newton, F equals ma. That force is going to be, when I release it out here, as it moves here, there's really only one force acting in the x direction, and that's going to be the spring. So that force is minus kx, is equal to the mass. The acceleration we're going to write as the second derivative of x with respect to time. We're going to just rearrange some terms here, and I'm going to get dx, the second derivative of x with respect to time, and 2 should be over here, minus k over m times x. This is going to be the kind of classic form for a differential equation that's going to describe simple harmonic motion. This particular case, we've got a constant here, and this is what we're going to want to look for, is a constant inside of here, and of this form. The minus sign will be here, and that there's going to be this minus comes from the spring. It's what we call a restoring force. It always wants to pull it back to the origin. When it's back here, it wants to pull it back this way. When it flies out there, it wants to pull it back, always pulling back to the origin. Now, right now, this is the differential equation. We need to solve for that, but this is a little tricky. We got the second derivative of x equaling some constant times x. So how do we get a solution? Well, I'm going to suggest that maybe simple harmonic motion solutions are valid. So what we can do is put them to the test. If x is equal to that and the second derivative is equal to that, maybe I can just stick them in there, and if I stick them all in and it's valid, I've got a solution. So rather than something you might do in a differential equations class, you might kind of bring them up from scratch. But very often we just kind of make a good guess. So for the second derivative, I'm going to take just this whole thing and stick it down here. And then I've got a minus k over m, and then for x, I'm going to take the x and stick it in here. And you'll notice a bunch of things cancel. Most importantly is that the cosine omega t plus phi, these two terms are going to cancel. If we're going to have an equality, this thing has to hold at all times. And so the fact that they cancel out of there, that takes time out of it, and it's not, we don't need to, we should have a solution. Now there's going to be some other things that cancel. We're going to get a minus there, and that cancels. And then we're still left with an omega squared, and we've got this k over m. That's the only thing that's left. So as long as omega squared is equal to k over m, we've got a solution. It works at all points in time. And so then I can say, these are the solutions to that equation. You can take the square root to get the square root of k over m. And then once we have omega, we can go back and stick them inside here, and we've got our solutions. There's some arbitrary constants. A is 1. It didn't really matter how far we stretched this thing. As long as, again, we don't exceed the elastic limits of the spring, we can get it to set. So this really is determined, the A, by our initial conditions. Also by initial conditions, this phi has to do with where you want to start your clock. If you stretch the spring all the way out here, and let's say I'm holding it there and then I release it, and as I release it I hit my stopwatch, so t equal to 0 is here, then it starts moving. If that's the case, then phi is just equal to 0. T equal to 0, cosine is 1. Phi would be 0, so that x would be out here at A. Okay, then once I have this, once I have omega also, then I can immediately get the frequency. 1 over 2 pi square root of k over m, or the period. Period is just 1 over frequency. That just flips that. Sometimes you get a little, with these reciprocals, it gets a little confusing between the two. You might think of like period. The period's going to be longer the bigger the mass, so that should sort of make intuitive sense. A big mass, it's going to have a slower, longer period. And then the force constant of the spring, if that's large, that wants to make this smaller. The period would be shorter. The higher frequency, this thing would oscillate more. So kind of learn to, as Dr. Young says, read the math. Okay. Now, how about if we take we call these massless, frictionless springs that are infinitely long, so we don't have to worry about exceeding their elastic limits. Let's say we want to connect a mass to a spring vertically. And at first it seems, well, wow, this could be different than it was on a frictionless tabletop going back and forth. The idea for something like this, it's important that we find the position of equilibrium. We're going to start off, let's say, with just hanging this spring, and it's just going to hang so that there's really no force on it. Again, we're assuming that spring has no real mass to it itself. This is an ideal spring. Then if I hang some kind of weight on it, it will hang down. And imagine it's just going to sit here. This is what we're going to call the equilibrium position. This is very similar to what we might do in Physics 121, where we say, oh, the force of the spring up. I'm just doing, the direction is up. In fact, I'm going to just for convenience, I'm going to call down positive. The upward force would be a minus kx. I've already indicated it's in that direction, so I don't want to do a double negative here. But essentially, this is just holding the weight of this thing, and it would just be balanced there. So it would be in front of you. These are the equilibrium positions. So this is very much like we did back in Physics 121. Some F equals ma. The acceleration 0, it's just sitting there. And then we've got a downward mg, and then a minus kx. Here I've got that negative there, is got to be equal to 0. And then we can come up with kx is equal to mg. This is a handy one for getting at, if you don't know what K is, but we put a mass on the spring and we measure how much it stretches. We can come up with the K, or the force constant, for that spring. But now we want to do something different. I want to set this thing into motion. So if it's balanced there and I pull it down and then I'm going to release it, it's going to start to oscillate. But it's not going to oscillate around the old x0 position. I call this initial stretch of the spring x0 for that stretch. But it's also going to stretch from that a distance x. So we're adding that a little bit there. So now the tension is going to be k x plus x initial, with my definition of x from the equilibrium. We're going to want to describe this motion. When I release it, it's going to go back and forth, and it's going to cross over that equilibrium point. And that will be our new 0, so to speak. Okay, in the dynamic sense, we just F equals ma. We're not setting it equal to 0. We're going to let this thing move. Ma, again, we'll use the second derivative with respect to time for acceleration. The sum of the forces are going to be mg, I'm calling down positive, minus k x plus x naught. And what we can do with this is, let me expand that x, the k through, so we have two terms here. Then we get a minus k over k times x over x naught is going to be equal to mg. So when I put that in there, these two are going to cancel. And we end up with really the same form for the differential equation. Now all we really need to do is, once we get it to this point, we say, then we've got the solution. We know simple harmonic motion is going to apply here. And so I know what the solution is already. And in the exam, you get a differential equation like this and you jump to the next line. Dr. Young is going to be cool with that. He says, oh, okay, you know your stuff. You know exactly what's happening. And you also know that omega is going to be equal to that constant, k over m. And so you can get your period. And if you want your frequency, you can get that. So things ultimately didn't really change much whether the mass was going this way or vertically. But at first, when you look at this, you say, wow, this is a weird-looking differential equation. And some of the homework problems and some problem that he might give you might have you need to solve for the equilibrium position and include it in your solution so that you can get the standard differential equation for simple harmonic motion. Okay, while we got a spring here, we can also, there's energy methods that can be handy. Just like in Physics 121, a lot of times you didn't have to use the force method. If you could use energy methods, wow, they usually were easier. The idea with energy methods, we'd maybe stretch this thing out. If you stretch it out and you hold it, that spring has a certain amount of potential energy. And you remember from back in 121, or maybe you don't, the potential energy of a spring is a 1/2 kx squared. So imagine I've stretched this all the way out here, so I'm holding it and I'm going to release it. It's at its maximum stretch. And if we release it, the kinetic energy would be 0. Okay, and, or I should say, the kinetic energy 0. When x is equal to the amplitude, that should be then the total energy of the system, once we have that. Okay, and in general, once I release it from here, then it's going to get set into motion, and it's going to have a combination, like I have here, of stored potential energy of the spring, but it also has some kinetic energy. So here the total energy in this is going to be 1/2 mv squared, the kinetic energy, plus the potential energy, and that should be the total energy. But the total energy was 1/2 Ka squared. So I set these two equal, and then that's your general energy equation. Let me come to this in a moment. And energy is going to be conserved or constant. And so we're going to use the idea that the time rate of change of that energy should be 0, since it is constant. So there's another way we can get at the differential equation. We can look at the energy. We take the energy here is all of that. We're going to take the derivative of that with respect to time. Well, this is the total energy. It doesn't change. So I expect taking the derivative of this should equal this should be a constant, and therefore the derivative should be 0. So I'm going to set that 0, and I'll take the derivative of this. This 2 is going to come down. The 2's are going to cancel, leaving me with an mv. But also, this is something that a lot of beginners forget. We're doing the chain rule. We're taking the derivative with respect to time. So we're going to have a dv dt term. So this is something that often gets missed. Then when you take the derivative with respect to time for the potential energy, the 2 comes down, cancels. We have a kx, but we must go one step further, not just kx, but we've got to go that the derivative of x with respect to time has got to be on there. Just the chain rule has to be there. And dx dt will be the velocity. So if this is equal to 0, these two velocity terms we can divide through and cancel, since it's equal to 0. And then we're left with this. And if we go one more step, we can put this now into standard differential form, or differential equation form. And as soon as we get to this point, we can announce that, hey, we know that this is simple harmonic motion, and we're going to get the same solutions that would apply when we use Newton's method. So it's kind of a big picture. Now, as far as doing another example, a lot of problems we have has to do with a kind of a rotational motion. Here we've got a physical pendulum is kind of a good general place to start. The idea that we can have a pivot here, maybe I drive an axis through here, and this whole thing is going to oscillate around that point. The center of mass would be off here. There's going to be a torque applied to this thing, and we're going to follow kind of the same basic thought process that we did for the mass on the spring, only we're going to be dealing in rotational terms. And most people are pretty rusty with this, like from Physics 121. It was the toughest topic of the whole semester, and it's been some time. Now we're called on to use that. So instead of using F equals ma, when we deal with torsional problems or rotational problems, we're dealing not with F equals ma, we're going to be using the sum of the torques are equal to not m but I, the moment of inertia, times alpha, the angular acceleration. Yeah?
Would he give us the inertia?
He would, just like he did in 121, he would give you the moment of inertia of any kind of shape that you had.
Okay.
Now, well, other than maybe using the parallel axis theorem, he loves that. So keep in mind, he might give you something like a disk that is, about its center at 1/2 mr squared, and then you might pivot it. Let's say if we had a disk here and we tried to pivot it around its center of mass, it would just sit there. But if this was a disk and its center is here, but I drive a nail through it up here, this whole thing could then oscillate around that point. And we'll be dealing with the torques are going to be around that point that it pivots. So parallel axis theorem is an important tool in dealing with that. In fact, well, we don't quite deal with it here. Now, the torque is due to gravity pulling down. There's going to be a torque there. Those of you, hopefully you remember that it's that force times the perpendicular distance. So that is going to be mg times, this is going to be d times the sine of theta. Or you can go more formally, torque is equal to r cross f. That would, r would be from here out to the center of mass. That would be r crossed into the force, gravity down here, times the sine of the angle between them. If r is out this way and mg, that theta, same angle as here, is going to apply, and so we'd have the sine of theta. So it would be the r, which would be d, times the force, times the sine of the angle between them. So this is where you need to kind of review your stuff from Physics 121 to make sure you're comfortable with this stuff. Usually what we'll do, though, when we do these kind of rotational things, as you'll see, we're going to need to use small angle approximations. If we need to whip this thing into shape as far as getting it into standard form for the differential equation. I've got my second derivative here. Ooh, I got a sine there. It sure would be nice if it was just a single theta, and theta in radians. So we're going to assume there's going to be small oscillations here for any of this kind of stuff. And so I'm going to rearrange my terms. I'm going to leave this second derivative on this side. I've got mgd. I'm going to divide through by I. Stick this minus out here. And now hopefully you see that, wow, this form of it looks the same as the form for the mass on the spring. We've got the second derivative equal to our constant here, theta. And we got a minus indicating it's a restoring torque. And we're going to have mgd all over I. This I would be the moment of inertia around that point. So again, it's depending what he might give you, you might need to use the parallel axis theorem to get that I. Probably should have emphasized this is I about this point O here. Once we have that, we can immediately say what omega is. It's got to be this constant here. Or excuse me, the omega has to equal the square root of this constant, which is that. Omega squared is equal to that. And then once we have that, we can immediately get the period, 2 pi over omega, and we write that out. So again, you don't have to, once you get it of this form, you know the solution. It's simple harmonic motion. And then we know what omega is. Well, we know omega, we know the period. We could also get the frequency from that. Okay, now let's do kind of a simple case. Simple case would be a simple pendulum. Rather than have the mass all here, they'd be all like, say, crunched down here at the center of mass, and it would be just a little simple little mass here on the end of a string, and it would be oscillating back and forth. So we should be able to get that really from this. So I really did a more general case for the physical pendulum, and then we can take a look at this. The D would represent the length of that simple pendulum. The moment of inertia, or just a point mass. This is something that students typically forget, that the moment of inertia is defined to be m times r squared. So it'd be the mass that you have here times r. R would be the length of this thing squared. Then we can go back inside this equation. We should say that it's going to be 2 pi square root of, we're going to have I, which should be equal to, it'll be m over L squared. Down here we've got mgd. D was equal to the length of the pendulum. The m's drop out, one of the l's drop out. We end up with the equation, again for small amplitudes, of the period of a simple pendulum. Now, in the book, they kind of do this one first, and they build up to that, and I've just kind of done it in reverse to hopefully convince you that this is just a special case of the physical pendulum. Okay, so what might he give to you on an exam? Okay, this is one that came, and this slayed a lot of people at the time. The idea that we've got a mass connected to a spring. This mass is going to roll on the table. Now, this is not a frictionless table. If it was frictionless, then this thing would just pull back and forth. This thing wouldn't even roll at all. There'd be no need for it. It would just slide and skid back and forth, and it would be just like a block on a spring. But in this case, we've got this thing as it's rolling out, it's moving out and then rolling back, and this is how it's going to be oscillating. So this is a more complicated look at it. Okay, so let's look at, there's different solutions, and I've got like about 4 of them floating around here. One that's given with the practice problems, I kind of regret that I did because it's a little bit tricky. I think this is going to be a little more straightforward. You're gonna feel a little more comfortable with this. The idea is we first set up our direction of motion. I'm calling positive in this direction. So the force of the spring is going to be pulling in the negative direction. This is what I want to be careful for, this idea of the rotation. I want to make sure I don't mess up my signs. The best way to do that is to say, well, if this is positive motion, this thing would have to roll this direction to make it plus. So in terms of rotation, I would call this the plus direction, around like this, if this is going to be the plus direction. So I want to make sure these two things relate. The friction, there's going to be friction here because we need that in order to get this thing to roll. Right now, the way I've drawn it here, this thing is actually in motion that direction. Even though I'm calling this the plus direction, it's in motion this way. It's being pulled by the spring. Now, in order to move that way, this thing and roll without slipping, it needs to roll around this direction, and we need a frictional force to get it to do that. So in this case, the friction needs to be pointing in this direction. So got to see that that's going to be opposite. Now, I'll have a thing more to say here, but so then we would say, well, we've got two forces acting, F equals ma. That's going to be a minus kx, and friction is going to be in the plus direction, and then that should be equal to the mass times the acceleration. Kind of the part from rotation that you're probably a little rusty with is, instead of F equals ma, it's the sum of the torques are equal to I alpha. The torque in this case is going to be, if this is the plus direction, F wants to get it to rotate in the negative direction. That's a minus F times R is equal to I alpha. And we've got both of these going on. I'm going to solve for F here. So F is equal to a minus 1/2 ma. And then I can take it back over to this equation and stick it in there and simplify some terms. So I've got this is with the minus here. We can bring this over to the other side to join that one, and we get a minus kx is equal to 3/2 ma. A we want to again cast as the second derivative, and then I've got a minus kx. I'll bring the m and the 2/3 over to the 3/2 over here as a 2/3. And right now I've got the standard classical form for the differential equation. So I've really got the problem solved. This is what I'm looking for. The second derivative is equal to minus some constant, that stuff that's in the bracket, times x. And so once I have that, I know immediately, oh, omega's got to be equal to the square root of that. And the period is going to be 2 pi over omega. And you're home free. You've got the solution to the problem. Now, What can be a little tricky here is deciphering which way you want this friction to point. Now, I was suggesting that this thing is actually back in motion this way, so this thing is rotating this way and friction is dragging you along. However, when it goes past equilibrium and it comes back and it's headed back this way, we want it rolling now in the plus direction. In order to get it to roll that way, friction needs to point back this way. So in that case, that would be in the negative direction. This should have been negative. But when we do that, this will end up being, instead of negative, positive. So actually this works either way, and it really doesn't matter what direction you put your friction. If you put it this way, this ends up plus, this ends up minus. If you make it back the other direction, this is minus, this ends up plus. You end up with the same solution. So hopefully that alleviates some confusion. There is confusion in these problems, and they can be difficult. This would probably be the most difficult problem on the exam if he decides to have you do that. Okay, now something that can be handy, I use this energy method for a spring. This can be a great way of coming up with a differential equation that can avoid all these things with signs. Kinetic energy is always positive. Potential energy is always positive. So it's kind of nice to do that. So let's do this with an energy method. The idea, conservation of energy, the time rate of change of the energy has to be 0. That's the fundamental idea. So I take the energy of this, 1/2 mv squared. Oh, now I do have to keep on track of all my forms of energy. This 1/2 mv squared is the translational kinetic energy back and forth. But we also need the rotational kinetic energy. Remember, that's the 1/2 I omega squared. Take a look at these in the form of them. Refresh your memory. That's would be the kinetic energy for rotation. And then the potential energy of the spring, 1/2 kx squared, is going to be included as well. So if I go through and, now it rolls without slipping. So usually we did this quite a bit when we were doing it in the 121. Omega has to be V over R, assuming it's not slipping. This is really the eye of a big disk. That's 1/2 m r squared. Typically these r's end up canceling. We get an r squared here, we get another one there, and they will cancel. And then that just simplifies. You end up with a 1/4 mv squared, along with a 1/2 gives you a 3/4 mv squared, plus the potential energy, be your kinetic energy, your total energy. And then we do that same thing where if the energy is conserved, the time derivative of it is conserved, or is set to equal to 0. So but be careful when you take the derivative. This is with respect to time. So we have a 3/4 m. Those are constants. Bring the 2 down. That's going to cancel there. You're going to be left with now v to the first power. But we need the chain rule. We need to go now dv dt. People forget that term. And then we do this one. The 2 comes down. They cancel. That's kx to the first power. But then again, the chain rule would be dx dt. Well, this is going to be the velocity, and we have the velocity here. It's equal to 0. We can go ahead and cancel those. And we've got the equation in this form. And then we can go put it in standard form. The second derivative is minus this and some constant times x. Again, we've got now the same differential equation. And we know what the solution is for omega squared. And once we have that, we can get the period for this pendulum. So this would be an alternate way of doing it. Nice thing again about energy is that all of these are positive quantities. The tricky thing is make sure you use the chain rule correctly. Okay, let's on to a new topic. You've got, as far as predicting these oscillations, You've got some in the homework that I would advise, looking at. They typically would represent one of the harder problems that you might put on the exam. So you might want to, after we get done here, you might want to strategize as far as what's the most likely thing he might do to you. Did that first. It's kind of the more difficult of the topics that we're dealing with here. Let's move on to wave motion. The idea of a wave is you have a little piece of the wave can be oscillating with simple harmonic motion, and we get a whole wave, which is a whole string of simple oscillators. But let's kind of deal with general wave motion. And what I like to do is get a mental image, and I'm going to use this kind of mental image a number of different ways. One is just thinking about a pond. If I come up here and I touch the pond, I'm going to send out some circular waves. And imagine I'm going to be taking and touching the pond with a constant frequency. The period will be the same for both of these, and then they're going to pass on. So I'm going to set out a whole series of them. Now, the idea of lambda is what we call the wavelength, and that is literally the physical distance between the crests of these waves as they're moving out. And then it's really a simple idea. Just distance is equal to velocity times time. The distance covered, imagine you're maybe sitting in a little boat here and one of the waves hit and you took note of it, you hit your stopwatch and you're timing it for the next one to come, and then the next wave will hit. That time between those waves is going to be what we call the period, capital T. The velocity would be the speed of that wave, and then the distance between these wave crests would be that wavelength. Usually we arrange this in this direction. Take this down here, 1 over t, and then we know that the frequency is 1 over t, and usually we write this as frequency times wavelength is equal to the velocity of the wave. Now, this idea we're going to use over and over again. This applies to actually any wave. But usually it depends on the medium what the velocity is. If it's a water wave, ripples on the pond, that's one velocity. If it's the speed of sound, it's another velocity. If it's the wave velocity of a string, it's that. So this is really kind of media dependent. And these two are really kind of reciprocals of one another if you think about it. The idea is, what happens to the wavelength when I go up in frequency? If I start doing this more often, what's going to happen to the wavelength? It's going to get shorter and smaller. If I decrease the frequency where I'm not, or lengthen the period, I'm putting a longer time between them, that's going to do what to the wavelength? Yeah, that's going to make that longer. So they, again, as frequency goes up, wavelength goes down, and vice versa. So most people are comfortable with that, but again, this is applicable to any kind of wave. Okay, now we're going to start to deal with some more complicated stuff. So let's deal with an idealized mathematical wave and set this in motion. We get this idea of some mathematical function, and in principle it could be any kind of function. I want to do something that's very similar to what we'll be doing later on when we get into relativity. It'll be a little different. This is sometimes called Galilean relativity, or we'll just call it this mathematical motion here. The idea if we've got some kind of a function here, and let me make a separate axes. I'm going to call this the x prime axes. I'm going to keep this green axes, the x-axis, I'm going to keep that fixed, or what we think of as fixed. And this is going to be set into motion. Let's see, maybe I can do that again. So see that thing come in. And so if I want to take this mathematical function and make it a function of x prime, this other axis, it's at rest in its own frame of reference. And we typically will give some x prime, some point here leads to some y prime or some function of that x prime. And if we want to be able to look at it from either this frame of reference or that frame of reference, this is where we'll get into this with relativity, a couple frames of reference. I can look at this, and let me put this up first. We're talking about a particular point on that wave, so we do it in principle for all the points, but there's going to be some x prime to this one, leading to some y value. These axes, by the way, are supposed to be just right on top of one another, and plus we're going to make, as this axis crosses here, we'll call that t equal to 0. That's when we'll start our clock. This whole thing is going to be moving with some velocity v, so it's going to move over this distance, v times t. If I want to talk about a particular point on that wave, I can address it either with x prime, or I can address it with x. And then there's just this simple relationship that keeps them together, is that I can come up with x prime, that's got to be equal to x minus vt, and that's going to leave this little bit that's left over. So what we can do with this idea is, if I take any function, and the y values are going to be the same since they're this, but I take some function that starts out with, in terms of x prime, and I make this substitution, that the result of this is a new function. This is kind of buried inside. Wherever you see an x, you go ahead and stick an x minus vt. That's going to describe the motion of this thing traveling in the positive direction. You could play it with the, let me put this down. So basically, if you have this minus sign here, the function moves to the right, moving in the positive direction. And if you have an x plus vt, and then the function is going to be moving in the negative direction. Okay, so let me go. Okay, hopefully you've got that. Now, we typically, other than in some homework problems, we don't make this substitution directly or try to avoid it. Things get a little complicated when we're dealing with something like a sine wave. A sine wave in the sine function, and this applies to cosines or any of the trig functions, we need to put, the variable has to be in radians. We can't have physical distances. If I go back to this is actually a physical distance. And you can't do something like, what's the sine of 10 meters? Okay, that should be bothering you. That's not quite right. You can say, well, you got a wavelength of 10 meters, but we need to translate that into, if we're going to use the sine function, we need to do it in terms of radians. So what we'll do is, we can, again, if we're looking at an actual wave, this could be like a cross-section of a water wave or a string wave moving here, that there will be a wavelength to it. And again, the wavelength is a physical distance. You can talk about so many meters or so many centimeters. But we need to realize that one wavelength, if we're going to translate it in terms of an angle, we'll do that. Full wave would be translated to a 2 pi. In general, if we're just out here at some distance x prime, we want to turn it into an angular measurement, maybe call it theta. We can do that, and we can get a relationship between them by just ratios, that 2 pi is to lambda as theta is to x prime, and or theta is equal to 2 pi over lambda times x prime. Now we can stick in a physical length, because this physical length and this is a physical length. The meters will cancel and everything's going to be in terms of radians. So we can do a simple function, which would be a sine theta. If we want to set that equation into motion, we can take this theta and we take all of this and put it inside here. And then that's going to be 2 pi over lambda times x prime. Now, since this is a physical distance, now I can stick in x minus vt here. because I've got this to correct it and give it in terms of radian measure. You want to work through this a couple times so you get comfortable with what we're doing. We take this, what I just have here. This should be a traveling sine wave. It should be traveling in the positive direction. There's a convenient way of writing this. We've got this 2 pi over lambda, which is kind of a pain to have to keep writing. We also have this still applies to us. So what I'm going to do is, if frequency times wavelength is velocity of the wave, I'm going to take that and put that in for velocity. So frequency times wavelength is that. And we're going to define something that you probably haven't seen before. It's actually kappa, the Greek letter. Is something called the wave number. And it's really, there's nothing physically significant. This is just for our convenience, so we don't have to keep writing this. We're just going to call this kappa, or the wave number, which is defined to be 2 pi over the lambda. So it's just get rid of that nasty thing and having to write that. So we can, but before I get rid of it, let me take it through here. So we've got this times x, and then this times the function. We've got that. We will have these wavelengths that cancel here, so things clean up nicely here. And then I've got 2 pi times the frequency. That should be equal to the angular frequency. Back here with x, I have that nasty 2 pi over lambda, and we're just going to have the simple kappa that we'll replace it with. So we have a sine theta kappa x minus omega t. And this is what we will use for a traveling sine wave. It's traveling in the plus direction. You want to look at the sign here. If it's negative, it's plus. If it's minus, it's going to be, so it's traveling to the right. If you have a minus here, boom. If you have a plus here, it's going to be traveling to the left or in the negative direction. So this is what you want to get used to as far as writing an equation for a traveling sine wave. It also applies to cosines. The whole argument, you could replace that with cosines or tangents or in any trig function. Okay, so this is, you want to remember. Okay, a traveling sine wave. We dealt with some like on the waves on a rope or a string. Get something oscillating, something like we did in the lab, get that moving. These waves are going to move. Now there's several types of motion. There's going to be a speed that the wave is traveling along in the direction of motion, but then also every point on that wave, this is point P, is going to be oscillating up and down. So here it's starting here, it's going up to here, and then it's coming back down through the equilibrium, coming back up. They're obeying simple harmonic motion. So as far as the velocities, we're going to deal with the velocity of this wave on the string. But we also have what will be the velocity of this, called this the transverse velocity. Transverse waves are those that are oscillating transverse to the direction of motion, either that way or that way. The velocity of this point on the wave going up and down, we can get if the y motion is equal to this, just describing this sine wave and the motion of it. The velocity up and down of any point here is going to be dy dt. Taking the derivative, we end up with this. I think the math is pretty obvious. And v sub y is the transverse velocity. And again, do not confuse this with the actual velocity via the wave that is going along the x-axis or in the x direction. So these are... Okay, as far as what determines the speed of the wave on strings, Dr. Young did a kind of a quick and dirty derivation. There's better ones using the wave equation, which he didn't do in the last parts of this chapter. a little more satisfying maybe to your more mathematical types. But it's just kind of a little physical argument that the idea that the traveling wave, let's say this is the little crest of the wave. Well, it's moving along with the wave, at least instantaneously kind of in motion. This is where get a little bit, it's a little shady. But the idea that we're assuming the tension is the same, and we are assuming all small amplitudes. Let's see if we can do this. And we're going to see why here. There's going to be effectively this tension pulling down. Since this is up here, the tension is along here, and they're both pulling down on this thing. And it's pulling into the kind of the center of what's going to be a kind of a circular motion. That'll be a centripetal force, 2 pi times the sine of theta. And this centripetal force for this thing, and imagine it's at least instantaneously, it's kind of rolling and moving in a circle, so that centripetal force is mv squared over r. We can set these two things equal, and we have this relationship. The mass of this thing really depends what theta is. We need to get a little piece, the mass of that, and we relate that back to theta. So the mass is going to be 2r theta. This r times theta is half of this, and so we have to take times 2 times mu. Mu is what? The mass per unit length of the string. That is mass per meter. So if you need the mu of a string, if you just take a 1 meter of it and you put it on a scale, come up with the mass of it, that is what we call mu. We make use of that, and so I'll end up putting that in for m. Oh, and also I'm going to have a theta and a sine theta. I want to use we're going to have small amplitudes. That's going to lead to small thetas. And so we're going to make use of small angle approximation. I can do that by putting that in. Oh, I guess I just canceled that. I just put these, back up a step here. Okay, so we just go ahead and substitute this in for the mass. We've got this, we've got a theta and a sine theta. Here's where I can use the small angle approximation to get a reasonable approximation what's going on. Got a bunch of things that cancel. The big thing is this theta cancels. And we end up with, when we solve for v, square root of t over mu. Okay, so this is going to be the velocity of a wave on a string. It's going to depend on the tension on the string. And also mu, again, the mass per meter of that string. And that's going to be the physical parameters of the velocity. Okay, in general, the idea of a speed of a mechanical wave. We really need to go back and look at each one of these things. We deal with things like sound. Its derivation is going to be separate. All waves, we essentially have this basic property. It's going to be the square root of kind of the elastic property. The idea of you have a large elastic force, like a stiff force constant, that means that wave is going to travel faster. It's going to want to snap back. There's also an inertial property. That's the mass that's difficult to get to move. And the larger that mass, the smaller the velocity. The smaller that mass, the faster the velocity. So again, with these two basic properties, you can sort of kind of maybe even guess what the speed will be. We just looked at the idea of strings. Again, the tension, this would typically be in newtons, and then this is going to be mass per length, or some mass per meter if we're using SI units. Sound, this is just asserted, and it's not really proven yet. We need to actually get into some thermodynamics before we can do this in general. Generally, this bulk modulus is sort of like Hooke's law, where I think of like a balloon. If you crush it down, it wants to spring back. And this bulk modulus is sort of like the force constant, almost like K for a spring. This is the springiness of the air that's inside there. And it also depends on the inertia of the density of the air. So this is, again, just kind of a general arm waving argument. We're not going to do much with it. I think there's a homework problem maybe later. In fact, I don't even think it's assigned. It's a problem from the, but this is not, we won't do this until we get back into thermodynamics. The velocity, when you get into thermodynamics, you can see that the velocity is going to be dependent on the temperature. And we have a crude idea of what temperature means, but we'll do more with that later. This is maybe one you just need to just kind of suck up and just remember. I don't know that he might expect you to do this. Generally, we deal with like at room temperature. Very often we say, room temperature is about 20 degrees Celsius. So if you make that 20 degrees Celsius, you get a 334 meters per second. And so you'll see in a lot of problems, you'll see the velocity of sound, 334. They didn't say too much about it. They maybe didn't say anything about temperature. If there's any doubt on the exam, what he wants you to do, you go up and ask him if he wants more accurate velocities for something like sound. Again, this 343 at about 20 degrees Celsius is a good one to just kind of have floating in your head. There was, as I said earlier, we had the discussion with Dr. Young on the phone. He was making up the exam, and he says, hey, maybe you should do this in your review tomorrow, like hint, hint, hint. This is actually one that is a homework problem. So maybe you try this, and it's usually some people need some help with it. The next one, I guess we'll get to another problem. But when he told me about the one he did, he said, I did that in class. Yep.
Is this chapter 16 or 17?
Oh, good question. This is going to be for on the wave, so this is 16. The next one, he's got one similar to this, only with sound, and then that's going to be in chapter 17. Yeah, good. So that's where you're going to find this. And this is a homework problem. So I think it'd be good. And I said when he told me the problem that he did, I said, oh, that's just like this one. He said, yeah. So being that people haven't always gotten this one, let's take a look at it. Again, this is a homework one. Congratulations if you got it. Okay, a rope of total mass m and length l is suspended vertically. Show that a transverse pulse travels with the length of the rope in time delta t equal to this. Okay, now he gives you a suggestion. First, find an expression for the speed of the wave at any point at distance x from the lower end by considering the rope's tension as resulting from the weight of the segment below that point. Ooh, all those words. Let's try to turn that into a picture. The idea that the wave would be hanging down. The idea of this wave pulse, I could take this rope that's hanging and I could wiggle it and it would send a wave that would go out along this thing. Now, the thing is, the tension is changing as we go up, as you'll see in a minute here. And so, therefore, the velocity is going to be changing as we go up. So this is going to be not an easy problem, or at least conceptually, it's not an easy problem. Now, the idea is I'm kind of following here. First, find an expression for the wave speed at any point on a distance x from the lower end. So I'm just going to say, okay, let's deal with a little section of string here as how it's going to be moving here. I'm going to take out just a certain length here, because at this point, if you think about it, if we kind of sever this thing, the tension of this thing is helping to hold up this x length here. And the longer this is, the more it's got to hold up. So it looks like tension is going to be weaker here, and it's going to strengthen as we go up higher and higher. And we need to come up with an expression for that. This is just the mass of this. They also state in the problem the total mass m and length l. So that means that mu, the mass per meter, has got to be m over l. This mass, m sub x, is just for that piece. So hopefully that makes some sense. Okay, let's, and then now the tension is holding this thing up. Mu sub x, the mass here, should just be mu, the mass per length, times that x, and then that should be the tension that's in that cord. Okay, so we can make use of this. V is equal to the square root of T over mu. That tension depends where we are, and again, that's going to be a function of x. Mu x times g. We've got the mu here, and the actual mu's cancel, so we end up with the square root of gx would be the velocity of this wave as it goes up this string. Okay, and the velocity, of course, is just dx dt, just kind of standard. And what we're going to do is, not real obvious, and this is what gets a lot of people, we're going to put this rearranged terms here. In fact, we'll call it separate variables. We're going to take the dt up there, bring the v down. Why do I want to bring the v down? It's the square root of gx. That way, on this side of the equation, I've got everything in terms of x. And then on this side, everything will be in terms of time. And so that's going to lead to the idea I can get the total time for this pulse to go up by integrating, adding up all my little dt's as this thing goes through little dx's on up the string. Okay, so that would give me my dt. Now I would also need to integrate this side, and I want to look at my limits here when t is equal to 0, because I'm doing this in terms of x. This is going to be 0 at where I'm going to start my pulse. X would start at 0, and then is going to go up to a distance L. So I need to just make these terms work together. So hopefully you see this. Typically, students, when they're seeing this for the first time, they'll say something like, I would have never thought of it, you know. This is the fundamental idea what we want to play with here. So kind of get your head around this if you can. And then we can just now, really, it's just do the math. You got a dx. Things get a little messy here. I'll leave you to go through that. But essentially, once you do the math here, you get this 2 times the square root of L over G, which is what we're supposed to show. So again, in the red here, kind of try to get your head around that idea. Even if you're weak with your calculus, you know, if you can get this thing stated, he's going to give you most of the credit if you don't quite get through that. But this isn't a real difficult one. But this typically students have some trouble with. But he's liking it. Okay. Now let's go to this 4. This is in the next chapter, which is chapter 18. This is actually 4:18. And when he told me, he said, I was looking at this one, I did it in the class, you know, this would be really good. You should review this, you know. And my reaction, and still my reaction, is this is number 4 in the chapter. And this is harder than the other one, which that gives you a magenta. Yeah. I don't get the author here. So it's probably worthwhile to look at here. Okay, he says, okay, the speed of sound in air in meters per second depends on the temperature according to the approximate expression. Okay, we had a better one before. They're kind of simplifying this. This is would be kind of a limiting expansion of that. Not to worry, this is just given as an equation. It's a linear one, which is better than the one with the square root. So at least that simplifies things a little bit, but still not enough to make it a number 4. So this is given where T sub C is the Celsius temperature. Okay, so we're going to be doing that. In dry air, the temperature decreases about 1 degree Celsius for a 150 meter rise in altitude. Okay. Okay, assume this change is constant up to an altitude of 9,000 meters. What time interval is required for the sound from the airplane flying at 9,000 to reach the ground? You see the kind of parallel with what we're doing? Only this is with sound instead of the wave on the string. This is on a day when the ground temperature is at 30 degrees Celsius. Okay. Okay, but forget the what if in a second here. We got enough to chew on. Okay, so what I'm doing first here, we really need to come up with a basic expression for the temperature in Celsius for depending on what altitude we're at. The y is the distance above going to be the distance above the ground. It is decreasing, decreases by 1 degree Celsius for every 150 meters up. So this is kind of the rate. In this problem, we're going to start at 30 degrees on the ground, and then we're going to be decreasing as we go up. So we really need to write this equation. This is where you read this, and then you write the math. And then we can take these two ideas and put them together. So they did this with V, and we're just going to put in the temperature from my little expression here into here. We can simplify the math a little bit, and it is a linear equation, which is nice. But this is the velocity, the speed of the sound, depending on what altitude you're at. What y value. We're going to go from 0 up to 9,000, or actually we should be going from 9,000 down to 0. The time should be the same regardless of what direction we go. And then v is equal to dy dt. And here's where I'm kind of doing the same thing, where the speed of this thing, dy dt, vertically, so this is in the y direction, we want to separate variables again. So what I did before, I brought the dt over to the other side, dy, and then v I bring down because that is a function of y. So I go ahead and I take all of this and put it in for v, and I've got my setup for my not for my integration. So let's look at delta t is going to be, I'm going to add up all these little dt's as we go up to 9,000 feet, or same as coming down. I guess I have it going up from 0 to 9,000. That time should be the same going up as it is coming back down. We need to do some integration here, and that's not terribly trivial. Delta t, of course, is just going to be the adding up of all these little dt's as we go up. And we need a u substitution for this. Probably we've got all of this, so let's just let u equal that. Then we need a du, so we take the derivative. This is constant. We've got a y here, so I would get a du dy. We're also going to deal some limits. I'll come back to these. So when we do the u substitution, we get the delta t is getting the du. I've got all of this stuff that came out. Hopefully you can see this and make sense of this. And I've got a u. I've got to, I changed the limits here. When y is equal to 0, I go back into here, set y equal to 0, that's 0, and then I've just got u is equal to 349.7. That comes in here for the first one. Y equal to, when I go up to 9,000 meters, u is equal to 313.3, so that becomes this other limit. So now it's just crunching the numbers, doing the math, and okay, also, hopefully it's not lost on you that du over u is going to be your natural log. That's why I was kind of using that for the u substitution. That was guiding me. And then we can do the math here, and we come up with 27.2 seconds, and that's the answer. So, again, stuff in the red box is kind of where we separate variables, how we can do that. So, wow, so you think that's a good number 4? I can just see students, they get this book does that. These first problems on some of these chapters, it's like so demoralizing. Somebody's going, I'm just in 6 hours on the first problem. Yeah, sorry. Okay, number 4. Okay, anyway, he thought it was good. Now they also say, okay, what if compare your answer with the time interval required if the air were uniformly at 30 degrees? Now that shouldn't be a major problem here. Basically, we're going to be dealing with the time is going to be the distance over the velocity. At 30 degrees, we've got this speed, so we divide that into 9,000, and we have 25.7 seconds to get up there, so there is a difference. We're going to compare those two answers. So this is trivial. This is not trivial. So, okay. So, did I mention the people that have downloaded the notes? These were added. You may have to delete the old one and go to the same link. It will call up the new upgraded file and see if you can get that to work, or work with somebody else to see if you can get those things. Anyway, that's these 2 pages. If you don't have them, Dr. Young did this, so this should also be in your notes. So, yeah.
The notes file sent what email?
Oh, Dr. Young should have sent it on the campus email to as a student. You should have one, and it was a link in an email that's going to take you to a Google Docs that's a PDF file. So all of these things will appear. They don't quite unfold like this, but the complete page as we leave it should be on there as a PDF file. Okay? Yeah?
You sent us a PDF file, so it's not a link.
That's right. I don't have it for this. These are, we've got some movies in here. The file size is really big for the actual PowerPoint slideshow. If you're really dying to have it, you can send me an email. I'll send it to you. But
So there's no link. There's only a PDF file.
there's a PDF file. There is a link. So if you get an email from somebody, you can share it with anyone. Just copy it and paste it. The link is rather cryptic. It's one of these ones, with the big long things that you couldn't possibly remember it if you wanted to. But essentially it comes down to that. It is just a link to the PDF file. You can either download it or a lot of people just look at it online.
Well, it's not in the email, where's the link? Yeah, you didn't send us the actual...
That's right. The link is in the email. So.
No, it's
No,
not.
he didn't attach it at all.
It's just an
It's
attachment.
just a
You just sent us
PDF.
a data,
Oh, he sent an attack.
data file, so it doesn't change when you upload it.
Yeah, it's no dynamic.
So we just send out a link.
Boy, I thought he sent the actual link. Now, when I update it and save it, as far as I know, the updates have been going through. We tried that earlier, but there was a problem. Connor he has an iPhone, and he had it, and he'd hit the thing, and then it would list the PDF file. But he was having trouble in that when he was hitting it again, it wasn't updating. If you have it maybe on a computer at home where you can trash the old one and hit the same link, you do get the new file.
I think the problem is Dr. Young sent us the PDF and updated, so he has to send us a new PDF.
Yeah, there would be, I think it still works because I didn't change the file link to that. We have tested it, and we tested it this morning. So it does work, but again, the iPhone saw the link and said, I don't need to download this again because you've already got it. And so it just sticks the old one up in your face. Try that. Essentially, the only real difference is the addition of these problems. So if you want to make note of that, Dr. Young should have done this in your lecture notes, and the previous one was the homework problem, which you can also look at solutions online if you want. If you're still wanting it at the end, I can maybe come up here. What I did with Connor is have a link to the link, and you can put in your email, and we'll just send them all that want to make sure that they get it. Okay? So, yeah, again, apologies for that. In the past, we've done this, and it works pretty well, but there are significant tweaks to it. Okay. Whew, okay. Just a kind of conceptual stuff. When we do get into sound waves, the idea that they're longitudinal waves, we get something like a piston, or typically more like a speaker, that is vibrating back and forth. This looks a bit like the plunger that we're using in the lab, but this thing is actually moving, meaning to move this thing back and forth. This is called the displacement. And as this piston moves back and forth, or I should say maybe the speaker cone is vibrating like this, it's sending out waves and they're traveling in a longitudinal direction. So this thing is compressing it, these compressional waves go out, and it comes back and keeps sending them. It's hard to kind of talk around this thing and try to visualize this in your head. The power of a wave. I'm just going to put this up here. They do it in the book. It's rather lengthy. There's probably better ways to get it. There are better ways to get at it, but this is going to be the power in a string wave. It was derived, and we use it some. Whether you will need it for the exam, I'm not sure. Let's just kind of look at the basics of it. The power, this is going to be, power is in watts. So many joules per second are going to be going out through this wave. And it depends on the mass density of this thing. The heavier this stuff, the more power it contains. It's proportional to the square of omega, hence the square of the frequency. So this is often true of most waves. As you go up in frequency, the power gets squared. It becomes considerably more powerful. It also depends on the amplitude. That's how much this displacement wave is changing, and then the velocity of the wave. So I'm just going to put it up there, put some of the things you might see, and you've got a lot of relationships to kind of jam in your head, and I'm not sure quite what to say, other than I want to try to cover all the bases. There's also power of a sound wave, which is generated also. That's a rather lengthy one. Something, though, you should keep in mind between these two is this is A for amplitude, where S was the displacement. Think of that speaker going, and typically this is something small going back and forth. This is the amplitude of the string. So this has also got an A in it. This represents, like, if we're thinking in terms of these tubes, the cross-sectional area of the tube. So you want to keep in mind that's area, this is amplitude. Now usually with sound, what we will do, rather than send it down a tube like we did in the lab, we're going to be doing some things with something that's probably more important, and this I think will be on the exam, or at least this part of it, that the intensity of a sound wave, how loud it is the power over the area. So many watts per square meter is going to be represented by the power, the energy traveling through some area. So the only thing that changes here when we divide by the area, that drops out, and so this is the expression. Again, my sympathies as far as, I guess I'd just be looking at this and say, okay, I'm going to cram it in for the exam and then forget it. Now, what you will typically see on the exam is the sound level. We'll talk about this in terms of decibels. So we come to the idea of the intensity of the sound wave. Primarily, I'm going to be focusing in here. This, for right now, I guess I should have just left that off of there. Okay, so that the intensity is the power over the area. Now, typically in the problems we're going to be doing is that those waves as they happen, let's say you've got some source, a bomb goes off, or maybe just you have a 100-watt speaker blast in full blast. 100 watts would be joules per second. That sound is going out. It's going to spread out as you get further away from it, and the sound is going to decrease in intensity as you get further away, a little quieter. It sort of should make common sense. We are assuming that all that energy is going out, which isn't super realistic, in that a lot of times this energy going out serves to heat up the air. It kind of loses some of its energy going out just and ends up a little hotter here. We will, for all the problems we're dealing with, assume that all that energy, if you've got a speaker with 100 watts, that 100 watt speaker is going, that 100 watts is going in all directions. What we want to focus on is the intensity of how many watts in a square meter is going to determine the sort of so-called loudness of the sound. Now, a real common one, this is just kind of a mathematical translation to put the intensity in a logarithmic scale, since it varies so widely from the I naught, which is the sort of the power that your ears can barely hear. That is, if you haven't been to too many rock concerts, that this sound is very quiet. 10 to the minus 12th is going to be, if you're in a sound room, you should be able to just, if your hearing is great, you should just hear that. That's sort of the threshold of hearing. Or it can go up to some real large value, which we'll look at in a minute here. But this is just going to be the sound level, in beta. It's going to be measured in decibels, and it's a real common thing you're going to see in engineering. So what we want to do is be able to translate a problem with some intensity to be able to get what its decibel rating would be. Or more typically in a problem, he would maybe give you this. Sound level 1 meter from its source is 120 decibels. Okay, so this is a loud sound. It'll do damage to your ears. What is the sound level 15 meters away? Okay, so it's going to spread out more. It's not going to be quite as loud as it is when you're sitting 1 meter away from it. So what we first want to do is take that figure, 120 decibels. We want to get it into something we can deal with physically. So typically we want to put that into SI units. So we stick it in there. 120 decibels is this 10 decibels outside. That's just the way they made it. Natural log. This isn't a natural log, so this is base 10. I1 would be the intensity of the sound at 1 meter. We have to kind of determine where that is, because we have, again, turning that 120 into an intensity. This is the threshold of hearing that comes in here. So it really comes down to, we need to solve for I1. And so, let's say I divide here, 120 by 10. I've got this. This is the logarithms. You may be rusty with your logarithms. We get rid of all of this by taking 10 to this power. Logarithms really are just the power function. And so this will become 12. I'll take 10 to the 12th is equal to 10 to the log of all of that. That should just get rid of that log function. And so I just end up with 10 to the 12th, and then 10 to this is just all this stuff that's inside here. So jar your memory with logarithms if you need to. And then we can solve for the actual intensity. This is what is actually useful for us in terms of the physics. This is actually an intensity of 1 watt per square meter. Okay, so if you're sitting 1 meter away, this is 1 watt per square meter. And this is a loud sound, so your ears are sensitive. This is coming from some power from this source, and we need to now turn that into what power is being radiated here. This 1 watt per square meter is what the power, the intensity is when it hits them. It came from some source, like maybe a speaker or something, loud speaker. Now, it is power over area is the intensity. The area, you'll see the 4 pi r1 squared. This is the surface area of a sphere. If you think about this sound, it's going out in a spherical fashion. We want to know how many joules per second is going through a square meter of that sphere. So I'm dividing by the area of the sphere. That's where the power is passing through. And solve for the power, straightforward enough. Just solve for R solve for the excuse me, solve for the power from that. That should be clear. So it looks like it's 4 pi watts, or pi is about 3, so about 12 watts. It's a 12-watt speaker, you could say. Okay, so now what we want to do is now go out, after we get this information, we can do the problem. What about 15 meters away? This power spreads as it goes out over a larger sphere. So that's where I want to take that same power, which will be 4 pi watts, and divide it by the surface area of this larger sphere that's going to have a radius of 15 meters. Solve for the intensity, that is in kind of physics terms, watts per square meter, and we got this, 4.44 times 10 to the minus 3. Now, since the problem was stated in terms of decibels, I'm making the assumption, you could say, well, this is the intensity, I solved the problem. You did, but we want to translate that back into the same form that the question was asked. I want to turn this intensity into a decibel rating. So I go back into my decibel equation. It's going to be that is going to be 10 decibels times the log of the intensity over the I naught, the threshold of hearing. We can do that. Punch it all into the calculator, and I came up with 96.5 decibels then would be the sound at that distance. Okay, so this idea of using the decibels is it's used a lot, and as engineers you should not be thrown off by somebody talking about decibels and decibel ratings. Okay.